Kotlin fundamentals. We have learned to think about programming. Now we apply these ideas in a real language. This course uses Kotlin. Today we meet Kotlin and understand why it is a good choice for learning and for real applications. Kotlin is a programming language created by JetBrains and first released in 2016. It is a general-purpose language. You can build many kinds of software with it: mobile apps, server applications, desktop programs, web frontends. Kotlin is modern. It was designed recently, learning from decades of language design experience. It avoids many problems found in older languages. Kotlin is practical. It was built to solve real problems, not as an academic exercise. It is used by millions of developers in production systems. Today, Kotlin is the preferred language for Android development. Google officially recommends it, but Kotlin is more than an Android language. It works everywhere. Kotlin is statically typed. This means every value has a type, and the type is known at compile time. When you write code, the compiler checks that types match. If you have a function that expects a number and you pass a string, the compiler rejects it. Before your code runs, static typing catches errors early. The compiler rejects it. Before your code runs, static typing catches errors early. The compiler is like a first reviewer. It finds mistakes before users encounter them. Static typing enables tooling. Because types are known, the IDE can offer autocomplete. It knows what methods are available on each value. It can find all usages of a function. Some languages are dynamically typed. Types are checked at runtime. This is flexible but delays error detection. Kotlin chooses static typing for safety and clarity. Kotlin compiles to Java bytecode and runs on the Java virtual machine. The JVM is mature and battle-tested. It runs on servers, on desktops, on phones. It manages memory. It optimizes code as it runs. It provides a vast ecosystem of libraries. Because Kotlin runs on the JVM, it can use any Java library. Decades of Java libraries are available. You do not start from zero. Kotlin is also interoperable with Java. Kotlin code can call Java code. Java code can call Kotlin code. You can mix both in the same project. This is practical. Many companies have existing Java code. They can adopt Kotlin gradually, file by file. No need to rewrite everything. Kotlin is not limited to the JVM. Kotlin native compiles to machine code. It runs without a virtual machine. This enables iOS apps, embedded systems, and command line tools. Kotlin.js compiles to JavaScript. It runs in browsers. You can share code between a Kotlin backend, and a Kotlin multi-platform lets you share business logic across platforms. Write once, use on Android, iOS, web, and desktop. The language is the same. The platform differs. This flexibility makes Kotlin valuable beyond any single ecosystem. Kotlin was designed with safety in mind. Null safety is built into the type system. Types are non-nullable by default. If a value might be absent, you must declare it explicitly. The compiler enforces null checks. This eliminates the most common source of crashes, the null pointer exception. In Kotlin, you cannot accidentally use a null value without checking. Kotlin also favors immutability. The recommended way to declare variables uses val, which cannot be reassigned. Mutable variables exist but require conscious choice. Smart casts reduce repetitive code. When you check a type, the compiler remembers. You do not need to cast again. These features make code safer without being annoying. Safety is the default. Danger requires explicit choice. Kotlin reduces boilerplate. Type inference means you often do not need to write types. The compiler figures them out. You write less, the compiler understands more. Data classes generate equals, hashcode, toString, and copy methods automatically. One line replaces dozens. Default and named arguments reduce the need for overloaded functions. One function handles many cases. String templates let you embed expressions in strings directly. No awkward concatenation. Kotlin removes the ceremony found in all the languages. The code you write is the code that matters. A Kotlin file ends with the extension .kt. The file contains functions, classes, and other declarations. There is no required wrapper class like in Java. The entry point is the main function. When the program runs, main executes. A simple program, fun main opening brace, println, hello Kotlin, closing brace, that is a complete program. No boilerplate, no ceremony. The code does what it says. Functions are declared with fun. Classes are declared with class, bisbal, variables with var. The syntax is clean and readable. Kotlin has a philosophy, pragmatic over dogmatic. Kotlin does not enforce a single paradigm. It supports object-oriented programming, it supports functional programming. Use what works, safe over sorry. The defaults prevent common mistakes. You can bypass safety when needed, but you must be explicit, concise over verbose, reduce noise, express ideas directly. Let the compiler handle the rest, interoperable over isolated. Work with existing code, work with existing tools. Integration is not an afterthought. This philosophy makes Kotlin productive. It helps you write correct code quickly. Let us summarize. Kotlin is a modern, statically typed language. It runs on the JVM and can use all Java libraries. It also compiles to native code and JavaScript. Safety is built in, null safety, immutability by default. Syntax is concise, type inference, data classes, smart casts. The philosophy is pragmatic, safe, and interoperable. Kotlin is an excellent choice for learning and for building real applications. Variables and values. Every program works with data. That data needs names. We call these names variables. Today we learn how Kotlin handles variables and the important distinction between values and variables. A variable is a named container for data. You give it a name, you put a value in it. Later, you use the name to access the value. Variables connect names to values. When your code says count, the runtime knows what count means because you defined it. In Kotlin, declaring a variable looks like this: a keyword, then the name, then optionally the type, then the value. But not all containers are the same. Some can be changed, some cannot. Kotlin makes this distinction explicit. The keyword val declares an immutable reference. Once you assign a value to a val, you cannot reassign it. The name is bound to that value permanently. Val count equals 10. Later, you cannot write count equals 20. The compiler rejects it. This is the preferred way to declare most variables in Kotlin. Why? Because immutability makes code easier to understand. You see a val, you know it will not change. You can trust it. When you read code with val everywhere, you know the values are stable, no surprises, no hunting for where a value was changed. Val does not mean the value itself is immutable. If you have val list equals a mutable list, you cannot reassign list to a different list, but you can add items to the list. The list. The reference is fi. The content might not be. The keyword var declares a mutable reference. You can reassign a var to a new value. Var count equals 10. Later, count equals 20 is allowed. Use var when you genuinely need to change a variable's value. Loop counters, accumulators, state that updates, but use var sparingly. Every var is a potential source of confusion. Reading code, you must track how the value changes. It makes reasoning harder. Ask yourself, does this truly need to change? Often you can restructure code to use val instead, a function that computes a result rather than accumulating in a var. A new val for each step rather than modifying one var. Start with val. Switch to var only when necessary. Kotlin infers types when possible. Val name equals Alice. What type is name? String. The compiler knows because you assigned a string literal. Val count equals 42. Type is int. The compiler infers it. You do not need to write val name : string equals Alice. The type is obvious from the value. Kotlin lets you omit it. This reduces boilerplate, your code is shorter. But the type is still there. The compiler knows it. The IDE shows it. You just did not need to write it. Type inference is not guessing. The compiler deduces the type with certainty. If it cannot, it asks you to provide the type. Sometimes you need or want to write the type explicitly. When there is no initial value, valName: string, you declare the type because there is no value to infer from. You will assign it later. When you want a specific type, val_ratio equals 3.0 gives double. But if you want float, you write val_ratio: float equals 3.0. When clarity helps readers, complex expressions might benefit from stating the type explicitly so readers understand immediately. When the API requires it, function parameters always need explicit types. The compiler cannot infer parameter types. The syntax is name: type, with the type after the name separated by a colon. Some values are truly constant, they never change, and are known at compile time. Const val declares a compile time constant. Const val pi equals 3.14139. This value is embedded directly into the code. No variable lookup at runtime. Maximum performance. Const val has restrictions. It must be a primitive type or string. It must be initialized with a constant expression. It cannot be a computed value. Const val must be at the top level or in an object. It cannot be inside a function. Use const val for true constants, mathematical values, configuration strings, fixed limits. These are values that are the same everywhere, always. For values computed once at startup, use regular val. For true compile time constants, use const val. Variables have scope. A variable exists within a certain region of code. A variable declared inside the function exists only in that function. Code outside cannot see it. A variable declared inside an if block exists only in that block, Kotlin uses lexical scoping. The position where you declare the variable determines where it is visible. Keep variables in the narrowest scope possible. Declare them where you first need them, not at the top of the function. This makes code clearer. The variable exists only where it is relevant. Names matter. Kotlin uses camel case for variables and functions. The first word is lowercase. Subsequent words are capitalized. Username, total count is valid. Constants in UPER, iSensei is-case, max iStice, default -timeout. Choose meaningful names. Count is better than C. Username is better than S. The name should explain the purpose. Avoid abbreviations unless they are universally understood. id, URL, HTTP are fine, ISFR and M is not. Good names make code readable without comments. Let us summarize. Val declares an immutable reference. Once assigned, it cannot be reassigned. Prefer val. Val declares a mutable reference. It can be reassigned. Use only when necessary. Type inference lets you omit types when the compiler can figure them out. Explicit types are needed for parameters when there is no initializer, or for clarity. Const val declares compile time constants. Keep scope narrow. Name variables clearly. Variables are simple, but using them well makes code clearer. Functions. We know how to store data in variables, but programs do more than store. They compute, they transform, they act. Functions are how we organize these actions. Today we learn to define and use functions in Kotlin. A function is a named block of code that performs a task. You give it inputs, it does something. It may produce an output. Functions let you reuse code. Write the logic once. Call it many times. No copying, no duplication. Functions organize code. Instead of one giant sequence, you have named pieces. Each piece has a purpose. The code becomes readable. Functions are the building blocks of programs. Small functions combine into larger capabilities. In Kotlin, you declare a function with the fun keyword. Fun followed by the name. Parentheses with parameters, optional return type, and a body. A simple function, fun greet opening parenthesis, closing parenthesis, opening brace, println hello closing brace. This function takes no input and produces no output. It just prints a function with a parameter, fun greet with name of type string. The parameter name has type string. When you call the function, you provide a value for name, a function with a return value, fun add, with a of type int and b of type int and b of type int, returning int. The return type is int, specified after the parameters with a colon. The return keyword sends the result back to the caller. The structure is fun name parentheses parameters colon return braces body. Parameters are inputs to a function. Each parameter has a name and a type. The type is required. The compiler needs to know what kind of data to expect. Multiple parameters are separated by commas, fun add with the int and bint. Inside the function, parameters are like val variables. You can read them, you cannot reassign them. When you call the function, you provide arguments. These are the actual values for the parameters. Add with 5 and 3 passes 5 for A and 3 for B. Parameters are how functions become flexible. The same function works with different inputs. A function can produce a result. This is the return value. The return type is declared after the parameters fun square with n int returning int. Inside the function, use return to send the value back, return n times n. When a function returns a value, you can use it in expressions value result equals square of 5. If a function does not return a useful value, its return type is unit. Unit means no meaningful return. You can omit it. Fun greet is the same as fun greet returning unit. Every function has a return type, either a meaningful value or unit. Many functions have a simple body, just one expression. Kotlin has a short form for these. Fun square with n int returning int equals n times n. No braces, no return keyword, just equals and the expression. The type can often be inferred. Fun square with n int equals n times n. The compiler knows the result of n times n is int. Single expression functions are concise. They show the essence, input, transformation, output. No ceremony. Use them for simple computations. For complex logic with multiple statements, use the full block form. Sometimes parameters have sensible defaults. In Kotlin, you can specify default values. Fun greet with name string equals world. If the caller provides a value, it is used. If not, the default is used. Greet with Alice prints hello Alice. Greet with no arguments prints hello world. Defaults reduce overloading. In Java, you might write 3 versions of a function for different parameter combinations. In Kotlin, one function with defaults handles all cases. Place parameters with defaults at the end. This allows callers to omit them positionally. When calling a function, you can name the arguments. Instead of add 5, 3, you write add a equals 5, b equals 3. Named arguments make code clearer. Greet name equals Alice, greeting equals hi is more readable than greet Alice hi. Named arguments allow any order. Create user email equals a@b.com. Name equals Alice works, even if name is the first parameter. Named arguments are especially useful with many parameters or default values. You can skip defaults, configure debug equals true sets only what you need. Use named arguments when it improves clarity. To call a function, write its name followed by arguments in parentheses. Greet parentheses calls the greet function with no arguments. Add 5, 3 calls add with arguments 5 and 3. The function executes. If it returns a value, you can use it. Val sum equals add 5, 3. Functions can call other functions. A function can be built from smaller functions. The call stack tracks which is active. When one function calls another, the first pauses, the second runs, then the first resumes. Let us summarize. Functions are named blocks of code that perform tasks. Declare with fun, name parameters, optional return type, and body. Parameters are typed inputs. Return type specifies what comes out. Single expression functions use equals for concise syntax. Default parameter values reduce the need for overloads. Named arguments improve clarity at call sites. Functions organize and reuse code. They are essential to well-structured programs. Control flow in Kotlin. Programs need to make decisions and repeat actions. We covered these concepts earlier. Now we see how Kotlin implements them. Today we learn Kotlin's control flow constructs, conditions, branches, and loops. In Kotlin, if is not just a statement, it is an expression. It produces a value. A statement does something. An expression produces something. In many languages, if is a statement. You write if else to execute different code. But you cannot use it as a value. In Kotlin, you can val result equals if condition then value a else b. This eliminates the need for the ternary operator. Some languages have condition $b. Kotlin does not need it. Regular if works as an expression. When if is used as an expression, the else branch is required. The expression must always produce a value. The value of the if expression is the last expression in the chosen branch. You can chain conditions with else if. If condition 1, do A. Else if condition 2, do B. Else do C. The conditions are checked in order. The first true condition wins. If none are true, else executes. As an expression, val grade equals if score greater than or equal to 90, then A else if score greater than or equal to 80, then B else if score greater than or equal to 80, then DK, else if score greater than or equal to 80, then CV. Each branch produces a value. The entire expression evaluates to one of them. For complex branching, consider when. It is often cleaner than long if-else chains. When is Kotlin's powerful branching construct? It matches a value against multiple options. Think of it as a superpowered switch. When value, then branch for option 1, branch for option 2, else default. Each branch checks if the value matches. The first match wins. Else handles all unmatched cases. When is also an expression. It produces the value from the matching branch. Val description equals when x1 arrow 1 2 arrow 2 else arrow many. Unlike Java's switch, when does not fall through. Each branch is independent. When can match more than exact values. Ranges. When n in 1 to 10 arrow small, in 11 to 100 arrow medium, else arrow large. Types. When objet is string arrow text is int arrow number, else arrow unknown. Multiple values when char vowel letters arrow lovers arrow else arrow consonant. Arbitrary conditions when with no value, where each branch has its own condition. X greater than 0 arrow positive, x less than 0 arrow negative, else arrow 0. When is flexible, it replaces many if-else chains with clearer syntax. For iterates over things, for iteming collection, use item. The loop variable item takes each value from the collection one at a time. Ranges for I in 1 to 5 prints 1, 2, 3, 4, 5. The range 1 to 5 includes both endpoints, until for I in 0 until 5 prints 0, 1, 2, 5. Includes both endpoints, until for I in 0 until 5 prints 0, 1, 2, 3, 4. Downward for I in 5 down to 1 prints 5, 4, 3, 2, 1. Counting down for works with any iterable, lists, arrays, strings, maps, and more. While repeats as long as a condition is true. While condition, body. Check condition. If true, execute body. Repeat. The condition is checked before each iteration. If false initially, the body never executes. Use while when you do not know how many iterations in advance. Read lines until end of file. Retry until success, wait until ready, make sure the condition eventually becomes false, otherwise infinite loop. Do while is similar but checks the condition after. Do body while condition. The body executes at least once. Then the condition is checked. If true, repeat. Use do while when you always need at least one iteration. Prompt user until valid input. Try at least once. The difference while may execute 0 times. Do while executes at least once. Sometimes you need to exit a loop early or skip an iteration. Break exits the loop entirely. The loop stops. Execution continues after the loop. Continue skips the rest of the current iteration. The loop continues with the next iteration. For I in 1 to 10, if I equals 5, break. Println I. This prints 1, 2, 3, 4. For I in 1 to 5, if I equals 3, continue, I des, prints 1, 4, 5. If I equals 3, continue, I des. Use break when you found what you need and want to stop. Use continue when you want to skip certain cases. These work in while and do while loops as well. Return exits the current function. It sends a value back to the caller if the function has a return type. Return can exit early. If a condition is met, return immediately. Do not continue with the rest of the function. A find function for I in list indices. If list at I equals target, then return I. After the loop, return null. The first return exits as soon as the target is found. No need to check the rest. Early return can simplify code. Handle special cases at the top and return. The main logic does not need nested ifs. Let us summarize. If is an expression in Kotlin. It produces a value. When is powerful branching, matches values, ranges, types, and conditions. For iterates over ranges, collections, and iterables. While repeats while a condition is true. Do while repeats while a condition is true. Do while runs at least once. Break exits a loop. Continue skips to the next iteration. Return exits a function, optionally with a value. These constructs give you complete control over program flow. Classes and objects. We have learned about data types and functions. Now we combine them. Classes let us create our own types that bundle data and behavior. Today we learn to define and use classes in Kotlin. A class is a blueprint for creating objects. It defines what data the objects hold. It defines what operations the objects support. Think of a class as a template. The class person might specify. Every person has a name and an age. The class also might define. Persons can introduce themselves. An object is an instance of a class. You use the class to create actual persons. Alice, age 30. Bob, age 25. Each is an object. Each follows the person blueprint. Classes let you model concepts from your domain. Users, products, orders, each becomes a class. Each instance is a specific user, product, or order. Declare a class with the class keyword. Class person with empty braces. This is the simplest class. It exists but has no properties or methods. Add properties to store data. Class person with var name, string, and var age int. Add functions to define behavior. Class person with a function introduced that prints I am name. Create an instance with the class name followed by parentheses. Val Alice equals person parentheses. Access properties with dot notation. Alice.name equals Alice. Alice.age equals 30. Call methods with dot notation. Alice.introduce parentheses. Most classes need initial values. The primary constructor provides them. The primary constructor is part of the class header, class person, with val name, string, and val age int. This creates a class with two read-only properties. Every person must be created with a name and age. Create instances by passing arguments val Alice equals person Alice equals person Alice 30. The val keyword makes properties immutable. Use var if the property should be changeable. Parameters without val or var are just constructor parameters. They are not properties. They disappear after construction. The primary constructor is concise. Most classes use it for their properties. Sometimes you need to run code during construction. An init block runs after the primary constructor. class person with val name string, then init block that prints created name. You can have multiple init blocks. They run in order, interleaved with property initializers. Use init for validation. Init with require that name is not blank. Use init for computed initial values, class rectangle with width and height, then init that sets area equals width times height. Keep init blocks simple. Complex initialization logic might indicate the need for factory functions. Sometimes you need multiple ways to create an object. Secondary constructors use the constructor keyword, class person with val name and val age, then constructor with just name that calls this with name and 0. This adds a second way to create a person, just with the name. The secondary constructor must call the primary constructor using this. Secondary constructors can do additional setup. They can have a body. In practice, default parameter values often eliminate the need for secondary constructors. Class person with name and age equals 0 achieves the same. Use the secondary constructors when default values are insufficient. Properties are more than variables. They can have custom getters and setters. Val creates a read-only property. It has a getter but no setter. Var creates a mutable property. It has both getter and setter. Custom getter var name string get returns field dot uppercase. This transforms the value when read. Custom setter var name string set value field equals value dot trim. This transforms the value when written. The field keyword refers to the backing field. This is where the actual value is stored. Use custom accessors for validation, transformation, or lazy computation. Many classes are just containers for data. Kotlin has a special form for these. Data class person with val name string and val age int. The data keyword generates useful methods automatically. Equals compares all properties. Two persons with the same name and age are equal. Hash code is consistent with equals. Data classes work correctly in sets and maps. To string provides a readable representation. Person name equals Alice. Age equals 30. Copy creates a modified copy, alice.copy with age equals 31. Data classes are perfect for value objects. Use them when identity is defined by the data, not by reference. Sometimes you need exactly one instance, not a class but a singleton. Object configuration with valmax users equals 100 and val app name equals myapp. This creates a single object named configuration. There is no class, just one instance. Access it directly. Configuration.max users. Object declarations are useful for global state, configuration, or utility functions. Sometimes you need static-like members in a class. Kotlin does not have static keyword. Instead, use companion objects. Class person with val name string. Then companion object with function create that returns person with that name. The companion object with function create that returns person with that name. The companion object belongs to the class, not to instances. Call it through the class name. Use companion objects for factory methods, constants associated with the class, or anything that should exist once per class, not once per instance. Let us summarize. Classes are blueprints for objects. They define properties and methods. Primary constructors define properties concisely. Init blocks run code during construction. Data classes auto-generate equals, hash code, toString, and copy. Object declarations create singletons. Companion objects provide class-level members. Classes let you model your domain with custom types. Inheritance and interfaces. Classes let us define types, but types often share structure and behavior. An employee is a kind of person. A manager is a kind of employee. Today we learn how Kotlin handles these relationships through inheritance and interfaces. Some concepts are specializations of others. A car is a vehicle. A bicycle is a vehicle. Both have wheels and can move. But they differ in details. Without inheritance, you repeat code. The vehicle code appears in car and bicycle separately. Changes require updating multiple places. With inheritance, you define the common parts once. Vehicle defines wheels and movement. Car and bicycle inherit these and add the specifics. Inheritance creates and is a relationship. A car is a vehicle. A manager is an employee. The subtype can be used wherever the supertype is expected. In Kotlin, classes are final by default. They cannot be inherited. This is intentional. Inheritance is powerful but dangerous. A subclass can break assumptions of the parent. Kotlin makes you choose explicitly. To allow inheritance, mark the class open. Kotlin makes you choose explicitly. To allow inheritance, mark the class open, vehicle. Now other classes can extend it, class : vehicle. The colon followed by the parent class establishes inheritance. The parentheses call the parent constructor. Without open, trying to extend the class produces a compile error. Kotlin protects you from accidental inheritance. A subclass can provide its own version of a method. In the parent, mark the method open, open class vehicle with open fun start. In the subclass, use override class car : vehicle with override fun start. The override class car : vehicle with override fun start. The override keyword is required. It documents your intention and catches errors if the parent method changes. You can call the parent's version with super override fun start super.start, then additional code. Overriding lets subclasses customize behavior while reusing the parent structure. Sometimes a class is too general to instantiate. You can say every shape has an area, but cannot define area for a generic shape. Each specific shape computes it differently. Abstract classes solve this. Abstract class shape with abstract class shape with abstract fun area returning double. The abstract keyword means this cannot be instantiated directly. Subclasses must exist. Abstract methods have no body. Subclasses must implement them. Class circle : shape with override fun area returning pi times radius squared. Abstract classes define what subclasses must provide. Interfaces define contracts without implementation. Interface: clickable with fun click. Any class can implement an interface. Class button : clickable with override fun click. Interfaces are like abstract classes but more flexible. A class can implement multiple interfaces. Interfaces can have default implementations. Interfaces clickable with fun click that prints default click. The class can use the default or override it. Use interfaces to define capabilities. Clickable means it can be clicked. Comparable means it can be clicked. Comparable means it can be compared. The interface says what, not how. A class can implement many interfaces. Interface clickable with fun click. Interface focusable with fun focus. Class button : clickable, focusable with override fun click and override fun focus. This is powerful. A button is both clickable and focusable. It satisfies both contracts. If two interfaces have the same method with different defaults, you must override and choose. Override fun common method with super angle bracket clickable angle bracket dot common method. Multiple interface inheritance is safe because interfaces have no state. Diamond problems are resolved explicitly. Sometimes you want to restrict which classes can inherit. Sealed classes allow inheritance only within the same file. Sealed class result. Class success with val data : result, class failure with val error : result. All subclasses must be defined in the same file. No other file can add subclasses. This enables exhaustive when expressions when result is success arrow use result.data is failure arrow use result.arrow, no else needed because all cases are known. Sealed classes model closed hierarchies. A result is success or failure, nothing else. An expression is literal, variable, or operation, nothing else. Use sealed classes when you know all the possibilities. Properties can be abstract or open to. Abstract class shape with abstract val name string. class circle, shape, with override val name equals circle. You can override a val with a val. You can override a val with a val. You can override a val with a var, adding mutability. You cannot override a val with a val, removing mutability. Properties can be overridden with custom getters. Override val name get returns my circle. The same open and override rules apply to properties as to methods. Inheritance is powerful but easy to misuse. Prefer composition over inheritance. Instead of employee extends person, consider employee contains a person. Keep hierarchies shallow. Deep inheritance is hard to understand. Use interfaces for capabilities. Use abstract classes for shared implementation. Make classes final unless designed for extension. This is Kotlin's default for good reason. Think easier carefully. A stack is not a list, even though they seem similar. Wrong inheritance creates fragile designs. Let us summarize. Classes are final by default. Mark open to allow inheritance. Override methods with the override keyword. Call parent with super. Abstract classes cannot be instantiated. They define what subclasses must implement. Interfaces define contracts. Classes can implement multiple interfaces. Sealed classes restrict inheritance to the same file, enabling exhaustive when use inheritance carefully. Prefer composition and shallow hierarchies. Kotlin type system. We introduced null safety concepts earlier. Now we see how Kotlin implements null safety through its type system. Today we learn the tools Kotlin provides to work with nullable types safely and effectively. In Kotlin, types are non-nullable by default. Val name string equals Alice. This cannot be null. Assigning null is a compile error. To allow null, add a question mark. Val name string question mark equals null. String and string question mark equals null. String and string question mark are different types. String always has a value. String question mark might be null. This distinction is the foundation of Kotlin's null safety. The type tells you whether null is possible. You cannot assign string question mark to string without handling the null case. The compiler enforces this. Think of question mark as asking, is there a value here? Sometimes yes, sometimes no. Why does this matter? In many languages, any reference can be null. You call a method, it crashes. Null pointer exception. The billion-dollar mistake. Kotlin moves null checks to compile time. If a type is non-nullable, the compiler guarantees it has a value. No runtime surprises. If a type is nullable, you must handle the null case before using it. The compiler forces you to think about absence. This does not eliminate null. It makes null explicit. You know where null can occur. You decide how to handle it. The safe call operator calls a method only if the receiver is not null. Name .length. If name is not null, returns its length. If name is null, returns its length. If name is null, returns null. No crash, no explicit if check. The operator handles it. Safe calls chain. User .address zitc address question. If any step is null, the whole expression is the result type is nullable. Name .length returns int ? Not int. Use safe calls when you want to proceed with null instead of crashing. The Elvis operator provides a default when the left side is null, name ? unknown. If name is not null, use it. If null, use unknown. Elvis is often combined with safe calls, name ? .length ? 0. Get length if possible, otherwise 0. Elvis can do more than provide defaults. It can throw name ? 0. It can throw name ? 0 exception. Elvis can return early valid name equals name ? return. The right side of Elvis executes only when needed. If the left side is not null, the right is skipped. Sometimes you know a value is not null, even though the type is nullable. The not null assertion converts nullable to non-nullable. Name double exclamation. If name is not null, this returns the value as a non-nullable type. If name is null, This returns the value as a non-nullable type. If name is null, this throws null pointer exception. Use double exclamation sparingly. It throws away null safety. If there are valid uses after a check the compiler does not understand in tests when you are certain, prefer safe calls and Elvis, use double exclamation only when you have no choice and are confident. When you check a condition, Kotlin remembers. If name not equals null, then inside the block, name is treated as non-nullable. No need for safe call. This is a smart cast. The compiler sees the null check and narrows the type. Smart casts, the compiler sees the null check and narrows the type. Smart casts work with type checks too. If obj is string, then inside the if obj is string, then inside the if obj is string. Smart casts work in when x is string arrow x.length is int arrow x plus 1. For smart casts to work, the variable must be immutable or local. The compiler must be sure the value did not change. Regular casts can fail. Val as string equals obj as string. If obj is not a string, this crashes. Safe casts return null on failure. Val as string question mark equals obj as question mark string. If obj is a string, s gets the value. If not, s is null. No crash. Combine with Elvis, val as string equals obj is obj's question mark string with dwell fault. Safe casts are useful when you do not know the type in advance. The let function helps when you have a nullable value and want to work with it if present. Name .let with lambda, then inside use the non-null value. Let takes a lambda. If name is not null, the lambda runs with the non-null value. If null, nothing happens. Inside let, you work with a non-nullable value. If null, nothing happens. Inside let, you work with a non-nullable value. Let is useful for side effects on nullable values. Send email only if address exists. Log only if message exists. Let us summarize. Nullable types use question mark. String is not string question mark. Safe call question mark dot returns null if receiver is null. Elvis question mark colon provides a default when null. Not null assertion double exclamation converts to non-nullable but can throw. Smart casts narrow types after null checks. Safe casts as question mark return null on failure. Let helps work with nullable values safely. These tools make null handling explicit and safe. Extension functions. Sometimes you want to add functionality to a class you cannot modify. The class comes from a library. You cannot edit its source. Kotlin has a solution, extension functions. Today we learn to extend existing types without inheritance. You use a class from a library. It does almost what you need, but it lacks one method you want. In Java, you might create a utility class with static methods. String utils dot capitalize with S. This works but feels awkward. The method takes the string as a parameter instead of being called on it. Inheritance might help, but only if you control instance creation, and many classes are final. Kotlin offers extension functions. You write a function that appears to be a method of the class, s.capitalize. But you define it outside the class, no modification needed. Define an extension by specifying the receiver type before the function name. Fun. String.add exclamation returning string equals this plus exclamation mark. String is the receiver type. Add exclamation is the function name. Inside, this refers to the receiver. Now you can call it like a method. Hello.add exclamation returns hello. The function is not actually added to the class. It is syntactic sugar. The compiler transforms it into a regular function with the receiver as the first parameter. But to users of your code, it looks and feels like a method. Inside an extension function, this refers to the receiver. Fun string.shout returning string equals this.uppercase plus 3 exclamation marks. This is the string the function was called on. If you call hello.shout, this is hello. You can often omit this. Fun string.shout equals uppercase plus exclamation marks. Methods are called on the implicit receiver. Use this explicitly when you need clarity or to disambiguate. You can also add properties to existing classes. Val string.wordCount int get equals this dot split space. Now you can write hello world dot word count and get 2. Extension properties cannot have backing fields. They must be computed. There is no place to store state. Extension properties are getters. Optionally with setters, they compute a value from the receiver. Use extension properties when the value feels like an attribute rather than an action. Extensions must be imported to be used. If you define an extension in a package, code in other packages must import it. Extensions can be defined at the top level, inside classes, or inside objects. Top-level extensions are the most common. They are available throughout the project once imported. Extensions inside a class are available only within that class. They can access the outer class's members. The scope controls where the extension is visible. Use it to limit availability when needed. What if a class has a member with the same signature as an extension? The member always wins. Members are not hidden by extensions. Class. Example, with FunGreet prints member. Fun example, greet prints extension. The extension is never called. This is intentional. You cannot use extension. The extension is never called. This is intentional. You cannot use extensions to hijack existing methods. Existing code remains safe. Extensions can only add new functionality, not replace existing functionality. This makes extensions predictable. You know the original class behavior is preserved. Extensions shine in several scenarios. Adding convenience methods to library types. String.isEmail to check format. List.second to get the second element. Domain-specific operations. Big decimal.format as currency. Date.isWeekend. Adapting types for your domain as recurrency. Date.isWeekend. Adapting types for your domain. Add methods that make sense in your context. Creating fluent APIs. Kotlin standard library is full of extensions. Map, filter, for each on collections. Let also apply on any object. Extensions can be defined on nullable types. Fun. String question mark dot or empty returning string equals this question mark colon empty string. Now you can call or empty on any string question mark, even if it is null dot file as string question mark equals null s dot or empty returns empty string. This is how many null safe utilities work. They extend the nullable type directly. Be careful, if the receiver can be null, you must handle it in the function. Let us summarize. Extension functions add methods to existing classes without modification. Use funReceiverType.name syntax. This refers to the receiver. Extension properties add computed properties. Extensions must be imported. Members always win over extensions. Use extensions for convenience methods, domain operations, and fluent APIs. Extensions can have nullable receivers. Extensions make Kotlin code expressive without modifying original classes. Lambdas and higher order functions. Functions are powerful, but so far we have defined them and called them. What if we could pass them around like values? Store them in variables? This is functional programming. Today we learn lambdas and higher order functions. In Kotlin, functions can be treated as values. You can store a function in a variable. You can pass a function to another function. You can return a function from a function. This might seem abstract. Why would you do this? Consider, you want to filter a list. The filtering logic varies. Sometimes you want even numbers. Sometimes you want numbers greater than 10. The pattern is the same. The specific check differs. You could write separate filter functions for each case. Or you could write one filter that takes the check as a parameter. The check is a function. Functions as values enable this flexibility. A lambda is an anonymous function, a function without a name. The syntax: braces containing parameters arrow body. Open brace x colon int arrow x times 2 close brace. This is a lambda that takes an int and returns it doubled. Open brace a colon int b colon int arrow a plus b close brace. Two parameters returns their sum. Open brace arrow println hello close brace. Two parameters returns their sum. Open brace arrow arrow. If there is one parameter, you can omit the declaration and use it. Open brace it times 2 close brace. The implicit name is it. Lambdas are expressions. They evaluate to a function value that you can use. Every function has a type. A function that takes an int and returns a string has type parenthesis, int close parenthesis arrow string. A function that takes two ints and returns an int has type parenthesis int comma int close parenthesis arrow int. A function that takes nothing and returns unit has type parenthesis arrow unit. You can declare variables with function types val double colon parenthesis int close parenthesis arrow int equals open brace it times 2 close brace. The type tells you what the function expects and what it produces. Just like other types tell you about values, function types make functions first-class citizens. They can go anywhere a type goes. A higher-order function is a function that takes functions as parameters or returns functions. Fun apply twice with xint, an operation of type int to int, returning int, return operation of x. A apply twice takes a number and a function. It applies the function twice. Val result equals apply twice 3 with lambda id times 2. Start with 3, double to 6, double to 12. Higher order functions abstract over actions. Filter takes a predicate function. Map takes a transformation function. For each takes an action function. You provide the specific behavior. The higher order function provides the structure. When the last parameter is a function, you can move the lambda outside the parentheses. List of 1, 2, 3 dot filter parentheses open brace it greater than 1 close brace close parentheses becomes list of 1, 2, 3 dot filter open brace it greater than 1 close brace. If the lambda is the only parameter, you can omit the parentheses entirely. Run open brace parentale, run open brace parentale, run open brace parentale. This makes code read more naturally. The lambda looks like a code block following the function. Trailing lambda is syntactic sugar. The meaning is the same. The readability improves. When a lambda has exactly one parameter, you do not need to declare it. Open brace x arrow x times 2 close brace can be written as open brace it times 2 close brace. It is an implicit name for the single parameter. This reduces noise for simple lambdas. Most collection operations use single parameter lambdas. Filter open brace it greater than 0 close brace. Map open brace it dot uppercase close brace. If you need a more descriptive name, declare it explicitly. Open brace number arrow number times 2 close brace. Use it for short, clear lambdas. Some lambdas have a receiver, like extension functions. The type looks like int dot parentheses close parentheses arrow string. A lambda with int as receiver, returning string. Inside such a lambda, this refers to the receiver. This enables DSLs and builder patterns. Apply, run, and with use lambdas with receivers. Val result equals build string open brace append hello semicolon append space semicolon append world close brace. Inside the lambda, this is the string builder. Lambdas with receivers make configuration code clean and readable. Return in a lambda behaves differently than in a function. A plain return in a lambda returns from the enclosing function, not just the lambda. To return from just the lambda, use a labeled return, return at for each, or return at for each, or return at filter. Alternatively, the last expression in a lambda is its return value. No return keyword needed. Open brace x arrow x times 2 close brace. The result of x times 2 is returned. Open brace x arrow if x greater than 0 then x else 0 close brace. The last expression is the result. Let us summarize. Functions can be values, store them, pass them, return them. Lambdas are anonymous functions, open brace parameters, arrow body close brace. Function types describe what functions accept and return, parentheses, int close parentheses, arrow, string. Higher order functions take or return functions. Trailing lambda syntax moves the lambda outside parentheses. It is the implicit name for single parameters. Lambdas enable flexible, reusable code patterns. Scope functions. Kotlin provides special functions for working with objects in a temporary scope. These are let, run, with, apply, and also. They seem similar but have subtle differences. Today we understand each one and learn when to use which. Scope functions execute a block of code on an object. They create a temporary scope where you work with the object. When the block ends, the scope ends. All 5 scope functions do similar things. They differ in 2 ways: how you access the object inside and what they return. Some use this to access the object inside and what they return. Some use this to access the object itself. Others use it, some return the object itself. Understanding these differences helps you choose the right one. Let passes the object as an argument to the lambda val result equals value dot let open brace it dot do something close brace. Inside the lambda, access the object using it or a named parameter. Let returns the lambda result. Whatever the lambda evaluates to, that is what let returns. Common uses null handling value question mark dot let open brace use it safely close brace. Transformations value dot let open brace transform it close brace. Scoping limit a variable's visibility to the lambda. Let is great for processing a value and producing a new result. Run makes the object the receiver of the lambda val result equals value dot run open brace. This dot do something close brace. Inside the lambda, access the object using this, which can be implicit. Run returns the lambda result like let. Common uses object configuration with computed result. Val length equals str dot run open brace uppercase dot run open brace uppercase dot run open brace. Running computations on an object. Run also exists without a receiver. Run open brace computes something close brace, just executes a block and returns the result. Choose run when you want receiver access and need the lambda result. With is like run, but the object is passed as an argument, not called on. Val result equals with parentheses value close parentheses open brace this dot do something close brace. It is not an extension function. You call with object open brace block close brace. With returns the lambda result. Common uses: working with an object when you do not need null safety. Grouping calls on the same object with config open brace setting 1 equals x semicolon setting 2 equals y close brace. Avoid with unnullable objects. Use run instead so you get the question mark dot syntax. Apply makes the object a receiver like run, but it returns the object itself. Val configured equals value dot apply open brace this dot property equals x close brace. Inside you configure the object. Apply returns that same object after configuration. Common uses: object initialization. Val user equals user parentheses dot apply open brace name equals Alice semicolon age equals 30 close brace. Build a pattern, build an object step by step, then use it. Apply is perfect when you want to configure an object and continue using it. Also passes the object as it, like let, but it returns the object itself, like apply. Val result equals value dot also open brace println value plus it close brace. Inside, you do something with the object. Also returns the object unchanged. Common uses: logging value dot unchanged unchanged. Common uses: logging value dot also open brace log dot debugs processing debugging chain dot also open brace println debug plus it close brace dot next side effects that do not change the object. Also is great for also do this without interrupting a chain. 2 questions guide your choice. First, how do you want to access the object? If you want this receiver, use run with or apply. If you want it argument, use let or also. Second, what do you want to return? If you need the lambda result, use let, run, or with. If you need the object back, use apply or also. The combinations let returns result, transform and produce new value. Also, it access returns object. Side effects in a chain. Run this access returns result. Compute something from the object. Apply this access returns object. Configure the object with this access returns result. Like run but not an extension. Null save processing with let, use a question mark dot let open brace save to database it close brace. Object configuration with apply, val button equals button, parentheses dot apply open brace text equals click, semicolon color equals blue close brace. Logging with also, data dot also open brace logger dot info, received, plus it close brace dot process data, computing with run. Val reversed equals text dot run open brace filter open brace it dot is letter close brace dot reversed close brace. Grouping calls with settings open brace volume equals 10 semicolon brightness equals 80 close brace. Each scope function fits naturally into these patterns. Use the one that matches your intent. Let us summarize. Scope functions execute a block on an object, let it access returns lambda result. For transformations, run this access returns lambda result. For computations, with this access returns lambda result. Non-extension form. Apply this access returns object. For configuration, also it access returns object. For side effects, choose based on how to access this or it, what to return, result or object. Kotlin collections. We learned about collections conceptually. Now we see how Kotlin implements them. Lists, sets, maps, mutable and immutable. Powerful operations. Today we master Kotlin's collection types and their operations. Kotlin has three main collection types. List, ordered collection with duplicates allowed. Access by index, first, second, third element. Set, unordered collection with no duplicates. Membership matters. Is this element present? Map, key value pairs. Look up values by key. Like a dictionary, each has two variants, read-only and mutable. Read-only you can read but not modify. Set, mutable you can add, remove and modify. Mutable list, mutable set, mutable map. Read-only is the default. Prefer immutability unless you need to modify. Create list of. Val numbers equals list of 1, 2, 3. Create mutable lists with mutable list of. Val mutable numbers equals mutable list of 1, 2, 3. Create sets with set of. Val unique names equals set of Alice, Bob. Create maps with map of. Val ages equals map of Alice to 30. Bob val ages equals map of Alice to 30, Bob to 25. It is shorthand for pair Alice. 30. Type inference works. List of 1, 2, 3 is list of int. The compiler knows. Access elements by index list bracket 0 or list.get0. First and last, list.first, list.last, safe versions, first or ends all, last or null, size, list.size. Is it empty? List.is empty. To contains list.contains element or element in list, find list.contains element or element in list. Find list.contains elements 1, index list.twined with con-1, null, index list.index of elements, well, it's of sublists, list.sublist 0, free, or list.take 3. For mutable lists, add, remove, clear, set. Sets focus on membership, not order. Create val set equals set of 1, 2, 3, 2. Result has no duplicate 2. Check membership element in set. Fast lookup. Set operations: union to combine, intersect for common, subtract for difference. Set A union set B gives all elements from both. Set A intersect set B gives elements in both. Set A subtract set B gives elements in A but not B. For mutable sets, add, remove, clear. Map store key value pairs. Access map bracket key or map.get key. Returns null if key not found. Safe access map.get or default key default. Keys and values map.keys gives all keys. Map.values gives all keys. Entries map.entries gives e-value pairs. Entries map.entries gives key value pairs. Contains key in map or map.contains key value. For mutable maps, put key, value, remove key, clear. Shorthand, map bracket key equals value for put. Filter keeps elements matching a condition. Val evens equals numbers dot filter, open bracket mod2 equals 0 close brace. Map transforms each element. Val doubled equals numbers dot map open brace it times 2 close brace. These are the most common collection operations. They work on lists, sets, and other iterables. Chain them numbers.filter open bracket greater than 0 close brace dot map open bracket times 2 close brace. Filter produces a smaller or equal collection. Map produces a collection of the same size. Both return new collections. The original is unchanged. Flat map, transform and flatten. Each element becomes a list, all lists combined. Val nested equals list of 1, 2, list of 3, 4. Nested.flatten gives list of 1, 2, 3, 4, group by, group elements by a key. People.group by open bracket.city close brace gives map of string to list of person. Associate, create a map from elements. People.associate by open bracket.id close brace gives map of long to person. Partition, split into two lists based on condition. Val evens and odds equals numbers dot partition open bracket mod2 equals 0 close brace. Reduce, combine all elements into one. Numbers.reduce open brace arc n arrow arc plus n close brace gives the sum. Fold, like reduce but with an initial value. Numbers.fold 0 open brace arc n arrow arc plus n close brace arc n arrow arc plus n close brace also gives the sum. Use fold when the result type differs from element type. Numbers.sum is cleaner than the reduce for addition. First with condition, last with condition, finds specific elements. Destructuring extracts components. For pairs, val key and value equals pair. For lists, val first, second, third equals list of 1, 2, 3. In loops, for key and value in map, use both. Data classes support destructuring. Val name and age equals person. Destructuring makes code cleaner when working with structured data. Use underscore to skip val name and underscore equals pair. Ignore the second component. Let us summarize. List, set, map are Kotlin's main collection types. Read only by default. Use mutable variants when needed. Create with list of, set of, map of. Mutable with mutable list of, etc. Filter selects elements. Map transforms elements. Flat map transforms elements. Flat map transforms elements into one result. Destructuring extracts components from pairs, lists, and data classes. Collections are fundamental to Kotlin programming. Sequences. Collections process all elements at each step, filter the entire list, then map the entire result. This can be wasteful for large data or when you only need some elements. Sequences offer a different approach, lazy evaluation. Today we learn when and how to use sequences. Collection operations are eager. They process everything immediately. List.filter.map.first. Filter processes all elements. Map processes all results. Then you take the first. For small collections, this is fine. For large collections, this is fine. For large collections, this creates waste. Imagine 1,000,000 elements. Filter creates a list of 500,000. Map creates another list of 500,000. You take one element, two intermediate lists for one result. The waste is memory. Creating large intermediate collections costs. The waste is time. Processing elements you never use. Sequences are lazy collections. They do not process elements until needed. They do not create intermediate collections. Sequence.filter.map.first, no intermediate lists. Each element flows through the chain until a result is produced. With sequences, elements are processed one at a time. Take an element from the source. Apply filter. If it passes, apply map. If you need more, take the next element. This is lazy evaluation. Defer work until results are required. From an existing collection, list.asequence. From elements, sequence of 1, 2, 3. From a generator, generate sequence 1, open brace it plus 1 close brace creates 1, 2, 3 forever. Using sequence builder, sequence open brace yield 1 semicolon, yield 2 semicolon, yield 3 close brace. Sequence of is like list of but lazy. Generate sequences creates potentially infinite sequences. Be careful, you must eventually stop consuming. The sequence builder gives fine control. You yield elements one at a time. Sequence operations are either intermediate or terminal. Intermediate operations return another sequence. They are lazy. Nothing happens yet. Filter, map, take, drop are intermediate. Terminal operations produce a result. They trigger processing. ToList, first, sum, count are terminal. Sequence.filter.map does nothing. It defines a pipeline. Sequence.filter map that does nothing. It defines a pipeline. Sequence.filtered map that elements flow through. Think of intermediate operations as building a plan. Terminal operations execute the plan. Collections process horizontally, all elements through filter, then all through map. Sequences process vertically, one element through the entire pipeline, then the next. Consider list.filter.map.take2. With the collection, filter all elements, then map all passing elements, then take two. With a sequence, process first element. If it passes filter and map emitted, process next element. Once take two has two results, processing stops. Sequences stop early. Once take two has two results, processing stops. Use sequences for large collections. The lazy processing avoids intermediate lists. Use sequences when you need only some elements. First take n, find benefit from early termination. Use sequences for chained operations. Multiple filter and map steps multiply intermediate collections in eager mode. Do not use sequences for small collections. The overhead of lazy evaluation can exceed the savings. Do not use sequences when you need indexed access. Sequences do not support random access. The rule of thumb, if you have thousands of elements or more, and you chain multiple operations, consider sequences. Sequences are not always faster. For simple operations on small data, collections are faster. The overhead of lazy evaluation hurts. For complex chains on large data, sequences win. No intermediate collections. Early termination. Benchmarks vary. The crossover point depends on data size, operation complexity, and how many elements you ultimately consume. Profile before optimizing. Do not assume sequences are better. Measure. Sequences shine when the savings from laziness exceed the overhead of laziness. Sequences can be infinite. Generate sequence 0, open brace, it plus 1 close brace, generate 0, 1, 2, 3 forever. You cannot call ToList on an infinite sequence. It will never finish. Use terminal operations that limit consumption. Take 10.ToList, first with condition, any with condition. Infinite sequences model unbounded streams, numbers without end, random values, input lines from a file, bod and. The laziness is essential. Without it, infinite is impossible. Let us summarize. Collections are eager. They process all elements immediately. Sequences are lazy. They process elements on demand. Create with asequence. Sequence off. Generate sequence. Intermediate operations build a pipeline. Terminal operations executed. Sequences process vertically, enabling early termination. Use sequences for large data, chained operations, and partial consumption. Avoid sequences for small data where overhead exceeds benefit. Sequences enable efficient processing without intermediate collections.